So in class, we've been talking about logarithms and natural logarithms and how to simplify different expressions and solve for basic exponents. And today we're going to start looking at different properties of logarithms, just like we looked at properties of exponents, to see how we can simplify different expressions. So our first property of logarithms is that for any base b, the log base b of 1 is always equal to 0. And if you think about changing logarithms back into exponents, we can always see why this is true. So what this is telling us is that b to the 0 power is always equal to 1, which is exactly true. Any number raised to the 0 power is always going to equal 1, which is why that logarithm property works. Same thing for the bottom one. Log base b of b is always going to equal 1. Because if you think about what this is asking, log base b of b, what that logarithm is asking for is what power of b is going to equal b? Well, b to the first is equal to b, so that would tell us that this has to equal 1. Our next property tells us that for any base b and any number n, log base b of b to the n is equal to n. And again, it's the same thing if you think about what that means as an exponential. So if we were asked to solve log base b of b to the n, if we wanted to solve that, we would loop around and we would say b to the x power is equal to b to the nth power. And we know that if we have equal bases, their exponents also have to be equal, so that's why it's equal to n. So in other words, whenever you see a phrase that looks like this, you can just cancel out the two bases and the answer has to be the exponent. Okay, so our next property is logarithm of a product. So this theorem tells us that for any positive numbers, x and y, because we can only take logarithms of positive numbers, the log base b of x times y is equal to the log of b of x plus the log of b of y. So you can split up multiplication inside of a logarithm to be addition of the two logarithms. And so let's think about why that would have to be true. So if we think about our exponent rules and what a logarithm really is, we're going to let log base b of x equal m and log base b of y equal n. So if we do our looping strategy, this tells us that b to the m power is equal to x and b to the n power is equal to y. So if we look at that log base b of x times y, we can really rewrite that to say, well, x is b to the m power and y is b to the n power. And we know from our exponent properties that you can combine things that have the same base when you're multiplying the bases by adding their exponents. So that's why we get addition of the two logarithms, because what log base b of x times y is asking us to say is what exponent would make base b equal to x times y. So it would have to be the exponent of m plus n. So that's why we can switch back and forth. So we can use that property to help us determine the value of logarithms without a calculator. So we know that log of 2 is approximately 0.301, and remember that's log base 10. And then log base 10 of 3 is approximately 0.477. So if we look at log of 6, well, 6 is just equal to 2 times 3. So using our logarithm of a product rule, we can split this into saying that, well, that's log of 2 plus log of 3. And we know the value of both of those, so we know log base 2 is log of 2, is approximately 0.301 plus log of 3 is approximately 0.477, which is approximately 0.778. So the log base 10 of 6 has to be approximately 0.778. Okay, and we can also do the same thing looking at log of 20. So I know that 20 is really log of 2 times 10. So I can again split that up using my logarithm of a product rule. So I know that the log of 2 from the problem is 0.301. And I know that log of 10, remember this is log base 10 of 10. So whenever the base and the value match, the exponent is 1. So this is 0.301 plus 1. which is going to give us approximately 1.301. So just like we have a product rule for logarithms, we also have a quotient rule. So when you are dividing two terms inside of a logarithm, you can split that up to be the subtraction between their logs. And that is, again, if you think about what our exponent rules are, it's because when you divide things that have the same base, you subtract their exponents. So that's exactly where the rule comes from. So we can use this to help develop different formulas. So for example, if we know log base 3 of 10 is equal to W, and log base 3 of 7 is equal to Q, determine the value of log base 3 of 0.7. Well, I can say the log of base 3 of 0.7, that's really 7 divided by 10. So that means this is really the log base 3 of 7 minus the log base 3 of 10. Well, log base 3 of 7 was Q, and log base 3 of 10 was W. So we can then say the log base 3 of 0.7 has to be equal to the expression of Q minus W. Okay. Our last property rule for logarithms is logarithms of a power. And what it says is for any base b and any positive number x, because you can only take the logarithm of positive numbers, and for any real number m, where m is the exponent, log base b of x to the m is just equal to m times log base b of x. So in other words, this just tells you to bring the power down in front of the log. So we can use that to simplify different expressions. So for example, we know the natural log of 17, and remember ln is just equal to log base e, is approximately 2.833. And we want to find the value of these without using any sort of technology. So because we have this is raised to a power, we can bring that 10 down in front. So we can simplify the natural log of 17 to the 10th power to be equal to 10 times the natural log of 17. So substituting in what that value is, we have 10 times 2.833, which is going to give us 28.33 as our value. And again, doing the same thing over here, we know that the fourth root of 17 can be rewritten as ln of 17 to the 1/4 power. We're going to bring that power down in front. And again, then we're just going to substitute in. So we're going to do 1/4 times 2.833. So going off to the side because it says without technology, so we're going to do it by hand. So we're dividing 2.833 by 4. So setting up my long division, I put my decimal point on top. 4 does not go into 2, but 4 goes into 28 7 times. So subtracting, we get 0. We bring down the 3. 4 cannot go into 3, so we put the 0 up. Bring down the next 3. 4 goes into 33 8 times. We get 32 with a remainder of 1. So we could keep going, but if I bring down a 0, I'm going to get 2, so we have 8. So I'm going to say that this is approximately 0.708. Okay, we're just going to do 2 more examples to show you about how you can use these different properties and how you can use them in conjunction with one another. So in example number 3, we're going to write each logarithms as a single number. So that means we want to condense them into one single logarithm. So the first thing we have to look at is if we have any exponents to deal with. So because I have this 2 in front of my logarithm, I can work backwards using that power property, and I can say that's really an exponent of 2. So this turns into the log of 40 plus the log of 5 squared. But we know that 5 squared is really 25. And using our addition and product rule for logarithms, if I'm adding logarithms, I can turn it into the multiplication of a single log. And we know 4 times 25 is 100, so 40 times 25 is 1,000. And now remember, if we don't have a base written here, this is really log base 10 of 1,000. Well, that means 10 to the third power is equal to 1,000. So our answer is 3. So we can actually simplify it there. So that's what we're going to go ahead and do. So again, we're just going to use our properties on part B. So now we have fractions involved, but that's fine. We can deal with fractions. So when you have an addition and a subtraction, it doesn't matter which ones you do first, just like it doesn't matter in order of operations if you do multiplication or division first. So I'm just going to work from left to right. So since I have addition between my first two logs, I can rewrite that as their product. So this becomes log base 2 of 3 over 5 times 5 over 2 minus log base 2 of 3. And I would suggest that you only do one thing at a time so you don't make a silly mistake. Well, if I look at this, if I'm multiplying 3/5 by 5 over 2, I have a 5 in the denominator and the numerator, so they're going to cancel out. So we're left with log base 2 of 3 over 2 minus log base 2 of 3. So that means I want to do 3 over 2 divided by 3. But if I divide by 3, that's the same thing as multiplying by 1 over 3. Just quick changing that into a fraction. Again, I have 3 in the numerator and denominator, so they cancel out. So this becomes log base 2 of 1/2. So if we think about this, we want to think 2 to what power equals 1/2. Well, this is 2 to the first in the denominator, and if I want to put a number into the denominator, I just need a negative exponent. So that tells me my power is really -1. You can use these properties with natural logarithms just like you can with regular logarithms, because remember, a natural log is just log base e. So we're going to do this same thing one more time in example 4, just using natural logs. So I have a coefficient in front of a logarithm, which means I first need to change that into being an exponent. So this is becoming natural log of t to the 1/3 plus ln of 5. And we know that the 1/3 power is really a cube root, so I'm just going to change that to be a cube root of t in here, plus the natural log of 5. We are adding between our logarithms, so that means we multiply inside. So this is going to turn into the ln of 5 times the cube root of t. Okay, so you have these 5 OYO questions to do. So for each question, you have 2 parts. In part A, you're going to rewrite them as the logarithm of a single number, so it should be log of just a single value. And then in part B, you're going to use that expression to simplify it without using a calculator, so just like we did on that last slide.